Okay, now we're going to start some other paradigms. Actually, we've been talking about paradigms, but we're going to talk a little bit more about different paradigms until we get to memory. It's going to be exciting because these are paradigms that have had a lot of influence, as you will see, and that are also influencing the systems we design. We're going to start with VLIW, which is an interesting philosophy. But before that, I'll just remind you what we have covered in the last month, let's say. Basically, we've covered a lot, as you can see. Microarchitecture, pipelining, precise exceptions, out of order, superscalar execution, branch prediction. So hopefully you're all familiar with these concepts now. They're all very high impact concepts. They're all employed in modern processors. But we're going to switch gears today. Slowly switch gears to VLIW and then talk about more specialized architectures. Does that sound good? Okay, everybody comfortable with these concepts? Sounds like fun. Yeah, I think it's fascinating, but there's more to be fascinated about. This is what we will cover today and tomorrow and next week, basically. Today, I intend to cover VLIW and systolic arrays. We won't have time for decoupled access and execute. That'll be a premiere of a lecture. And then tomorrow we'll do SIMD processing, and next week we'll cover GPUs. And then start memory, which is really the biggest bottleneck that we're facing. So, okay, what is VLIW? VLIW stands for very long instruction word, and then architectures. Essentially, it's a different ISA, instruction set architecture. It builds upon the von Neumann model, but it slightly modifies the von Neumann model such that an instruction is defined in a different way. So you can think of this as a variant of a von Neumann model. An instruction is defined to encode multiple operations, basically. Okay? So if you remember the superscalar execution concept that we discussed last week, superscalar execution, hardware was responsible for fetching instructions, multiple instructions, and checking dependencies between them. And then it executes, decodes multiple instructions, executes multiple instructions, and finishes multiple instructions. So it's basically a multiple instruction fetch, decode, execute paradigm, but hardware is responsible for doing all of this, right? What the compiler generates is sequential code as we would expect in a von Neumann architecture, right? It's essentially what we've been used to, except hardware extracts parallelism out of it every cycle. Okay. So everybody's familiar with superscalar, right? In VLIW, we do essentially the same thing, except the responsibility belongs to the software, meaning compiler. Compiler is responsible for identifying and packing independent instructions in a larger bundle. And it guarantees that these instructions that are put together are independent of each other. And these instructions can be fetched, decoded, executed concurrently, and finished concurrently. That's the idea. So these paradigms differ in terms of whose responsibility it is to find dependence or independence between instructions. Superscalar says, compiler doesn't need to do anything. I'm going to find all the dependencies. VLIW says, hardware doesn't need to do anything. Compiler is going to find all the dependencies. That's the idea, basically. And this actually makes a huge difference in terms of the success of these two different things. Superscalar is very widely employed everywhere. VLIW, not so much, although it has influenced a lot of things, as we will discuss, especially in compiler optimizations. So it's a different kind of success that VLIW brought into our collective knowledge of how to really design computers. It's really how you design the software stack, even though computers underneath may not be executing instructions in a VLIW way exactly. Okay, so basically, it's the responsibility of the software to find independent instructions and pack them together. Now the hardware becomes very simple. It fetches, executes the instruction in the bundle concurrently. It doesn't need to check dependencies between those instructions. In fact, VLIW goes another step. It's not just vertically what you're fetching in one cycle. It's also horizontally what you're fetching in multiple cycles. VLIW says hardware should not do any dependence checking. Basically, if you fetch another instruction in a previous cycle, it's the compiler's job to make sure that the later instructions can go into the pipeline without any dependence checking in hardware. That's the pure VLIW concept. Pure VLIW is very hard to achieve, of course, because you know that it's very difficult to have a lot of independent instructions. I'm going to give you a flavor of it today and also discuss the difficulties. But basically, there's no need for hardware dependency checking between concurrently fetched instructions in the VLIW model. And in the real pure VLIW model, there's no need for dependency checking at all. Hardware gets exposed. So there's some hardware, pipelined hardware, multiple instruction fetch vertically every cycle, and then horizontally a pipelined hardware. And it's the compiler's job to decide what gets executed in which cycle and in which slot in the pipeline. So basically the mindset is simple hardware, complex compiler. This is very different from the mindset that we've looked at in the last several lectures, right? We basically made hardware more and more and more and more complex, right? Out of order execution is actually very complex. You can think of VLIW as putting the responsibility of finding all of the independent instructions out of order and superscalar to the compiler. Basically, VLIW is the equivalent of out of order superscalar execution, where the software schedules the instructions, not the hardware. Does that sound good? Basically, that's the concept. That's really the most important thing that you need to know about a VLIW machine. Everything else is how do you make it work? Making it work is very difficult, basically. Okay, so pictorially, it looks like this, basically. This is the VLIW concept. You have a program counter. When you get to that program counter, you don't get a single instruction like we used to. You don't just get add, but you actually get 4 instructions in this particular case. And the compiler packed them together in memory, and compiler ensured that these instructions have no relationship or no dependence on each other, so they can be executed completely concurrently without the hardware doing anything other than executing them. In fact, the compiler also knows the structure of the hardware such that it knows that, for example, this processing element in hardware can execute loads. So the load instruction actually is aligned such that when you fetch it, you go to a decoder, and the decoder directly feeds the memory unit. So if there was no memory unit over here, for example, the compiler would not put the load in this location. If there was a memory unit over here, the compiler would do load in this location. Make sense? So the compiler, basically the philosophy is compiler knows the structure of the pipeline and the hardware, and it basically bundles the instructions together such that the hardware doesn't need to do, well, almost anything, if you will. Dependency checking for sure, but not even routing the instructions to the correct location, to the correct processing element where they can be executed. And that's the philosophy. And this philosophy was, let's say, first expressed explicitly in this paper. It's a beautiful paper. If you're interested, you can read it. We don't have any readings. Your books don't cover this concept. I think it's sad they don't cover this concept, but we will see. So I will give you hope that this concept may arise into the future, maybe 10 years down the road, again, because of some developments in machine learning. So compilers may not be as strong today to enable this, but 10 years down the road, if they're equipped with much stronger machine learning techniques, this discovery of parallelism can be much stronger 10 years down the road. You can use this as a prediction and see if I'm correct 10 years down the road. Okay, so conceptually, as you can see, it's beautiful, right? Simple hardware, complex compiler. Okay, so let's go into a little bit more depth. So a very long instruction word consists of multiple independent instructions packed together by the compiler. Packed instructions can be logically unrelated. And this is the key distinguishing factor of VLIW compared to what we will see tomorrow. Tomorrow, we'll see single instruction, multiple data architectures, vector processors which GPUs build on. They also can fetch multiple instructions per cycle from the same program counter, except those instructions are completely related. They all do the same thing. Here, if you look at this picture, these instructions are completely different. One is an add, one is a load, one could be a square root if you have that instruction. They don't have to have any relationship at all to each other, except, of course, they need to be executed by the program in that vicinity, right? But in SIMD or vector architectures, we will see tomorrow, you do the same thing. This picture, actually, I'm going to contrast tomorrow. This picture will be add, for example. All of them are going to do adds, except they're going to operate on different data. Okay, so this is something to foreshadow. And the main idea of VLIW, which we've discussed, is compiler finds independent instructions and statically schedules them, or packs or bundles them into a single VLIW instruction. Remember, we discussed static scheduling versus dynamic scheduling. This is completely static, meaning hardware doesn't need to find independent instructions like we did with out-of-order execution or superscalar execution. So traditional characteristics of VLIW, basically you fetch multiple instructions, you execute them, and you have multiple functional units. This is very similar to superscalar, as we discussed. Different from superscalar, all instructions in a bundle that you fetch together are executed in lockstep, meaning all of them start and complete at the same time. This is to make sure that the compiler can schedule instructions based on the pipeline structure. So you cannot really proceed. If one instruction is complete earlier, you cannot proceed, basically. And the compiler needs to take that into account. This makes scheduling easier at the compiler level, but also makes performance worse, as we will see. And finally, I already mentioned this, but instructions in a bundle are statically aligned to be directly supplied to their corresponding functional units. So a compiler knows the structure of the processor, and it can do this easily. Okay, let's take a look at a VLIW example in the ideal case. So here, I'm assuming two white bundles. This is actually the same example that we looked at in-order processor and then superscalar processor, and then now it became VLIW. This is bundle one. The compiler figured out that they're independent and it put them together. This is bundle two, and this is bundle three. And compiler did all of these. And then hardware is beautiful. Basically, you have two white fetch engines. There's no dependence checking. It is not shown over here. But basically, all of these bundles can be executed in a pipeline manner. And ideal IPC is clearly two instructions in a VLIW word, if you will. So you get two instructions per cycle. If the compiler was able to fill all of those slots, that's great. And as I said, compiler needs to do this horizontally, vertically every cycle, and horizontally across the pipeline stages. Okay, we can have a more sophisticated example. You will see that in your homework, and it's going to be fun. So, okay, let's talk about some of these characteristics a little bit more. So there's lockstep. In other words, all or none, all or nothing execution. If any operation in a VLIW instruction stalls, all concurrent operations stall. This makes scheduling easier. And in a truly VLIW machine, the compiler handles all dependence-related stalls. As we discussed, hardware does not perform any dependency checking. And the issue is really, if you know the latency of all of these instructions perfectly at the compiler level, maybe you can do this. Because at least you can figure out which instructions take how long. And if all of the instructions are taking, let's say, 3 cycles, you put them together, right? Or maybe close enough cycles. Now, the problem happens when you don't know the latency of an operation. And this is, there are cases where we don't know the latency of an operation. We discussed multiply operation, for example. The latency of a multiply hardware unit can depend on the input to the multiply. If one of the inputs is 0, and if you detect that, the multiply can take 1 cycle. Very quickly, you set the output to 0. If neither of the inputs is 0 or 1, then you may actually need to take 8 cycles to do the multiplication, if it's a complex multiplication. So that's a dependence, right? So basically, the latency of an instruction is dependent on the input data. Does the compiler know the input data? Probably not. Not the exact input data, right? We've suffered from this problem in the past when we talked about branch prediction, for example. Can the compiler do branch prediction? Can the compiler fill the delay slot? Similarly, the compiler doesn't know the exact input data because it's compiling the program, and then the input data gets supplied dynamically while the program is running. As a result, the compiler may really not know whether the multiply instruction, one of the inputs of a multiply will be 0 or 1 or something else. So the compiler essentially doesn't know how long this multiply instruction will take. Now, that's not true for all instructions, clearly. For add instructions, that may not be true. It may always take 2 cycles, for example. Fine. But if there are enough multiplies in your program, now static scheduling becomes difficult. Should the compiler assume a 1-cycle multiply or an 8-cycle multiply? I don't know. What's the answer? Well, you do profiling, right? That's what we do with compilers. We've discussed that for static branch prediction before. The compiler does profiling, uses some input sets, and says, oh, 99% of the time, the input to this multiply is not 0 or not 1. As a result, I'm going to assume this multiply is going to take 8 cycles, 99% of the time. If the compiler is correct, that's great. 99% of the time, the code executes nicely. But what do you do in the remaining 1% of the time? Well, okay, maybe it's okay, right? In that case, it takes 1 cycle. And in that case, it's okay because there's some, there still needs to be some hardware support. Basically, that's what I'm getting at. If the instruction doesn't finish on time, there needs to be some hardware support to make sure that all instructions proceed at the same time. So basically, this dream of not having any hardware support to avoid any stalls, to even detect stalls is essentially a dream. It doesn't have any correspondence to reality, I would say. There needs to be some hardware support to stall the bundle if the compiler didn't predict the latency correctly, for example. And this becomes even worse. We're talking about a multiply. Multiply is not that bad. Let's talk about a load. Now, once we go to memory, let's say all hell breaks loose, right? And that's true with modern machines. A load instruction, how long does it take? The compiler, well, we're going to see the memory hierarchy soon, but the compiler may assume it's going to hit in the L1 cache. We're going to talk about all of those soon. It may take 1 cycle. If it doesn't hit in the L1 cache, if it hits in the L2 cache, it may take 10 cycles. If it doesn't hit in the L2 cache, if it hits in the L3 cache, it may take 80 cycles. If it doesn't hit in any of the caches, it has to go to memory. It may take 500 cycles. Now we have a problem at hand, right? Which one is going to happen? Well, this is where all hell breaks loose from a compiler's perspective, because compiler says, I'm going to profile the program. Fine, you profile the program. You try to figure out which load hits in which cache. Okay, this is very much input set dependent, clearly. Depends on what you input to the program. And can you get everything correctly? Maybe, if you're really lucky. Most of the time, you don't get all of those latencies correctly. As a result, your profile is very much not representative of what happens in real life. As a result, the code scheduling breaks. And this is the real big fundamental problem with this sort of statically scheduled machines, memory operations. We don't know how long a memory operation will take. As a result, it's very difficult to say the next dependent instruction can be scheduled, let's say 3 cycles later, 4 cycles later, 80 cycles later, or 500 cycles later. And there's a huge variation, as you can see, right? It's not like 1 or 8 in multiply. It's more like 1 to 500, or maybe 1,000. And in some cases, you may actually not even be in memory. You may actually need to get the data from the SSD. In that case, it's 10,000, 20,000 cycles, etc. So basically, this is the problem with static scheduling. This sort of variable latency operations, in other words, in parentheses, memory operations, cause a great problem to static scheduling. So the compiler doesn't know what to do, basically. So what do? The compiler assumes something. If the assumption is incorrect, you stall the machine. Who stalls the machine? It's not the compiler. It's the hardware. Because the hardware knows where the load is, where the data is, or where the data isn't initially, of course, right? So that's basically why this dream is a dream. This pure VLIW is almost impossible to build in real hardware. You have to have some stall signal saying, oh, this operation is taking longer than expected, so stall the entire bundle, stall the pipeline. Does that make sense? So it's beautiful, I think. It's good to understand these trade-offs between hardware and software. And this is the real reason, in my opinion, well, one of the biggest reasons why VLIW has not been as successful. It doesn't have this tolerance to latency, or variable latency, I should say, if I want to be more accurate. It has tolerance to latency clearly. If it knows absolutely every single latency in the machine, every single latency absolutely correctly, it can come up with a schedule, which may not be a bad schedule, given the compiler techniques that we're going to discuss. But all of those compiler techniques break down when you don't know the latencies, essentially, or when you have variable latencies. Okay, that's why I spend a lot of time on this slide, basically this last part. What about variable latency operation memory stalls? This is really the downside. Whereas in an out-of-order machine, this is very simple. I mean, simple in the sense that it doesn't affect performance as much, right? You don't have a dilemma, basically. In an out-of-order machine, what happens? A load takes 500 cycles, fine. Keep fetching instructions, buffering them. In the reservation station, some of them will execute, some of them may not execute. So the model handles it without any problem. The hardware cost may increase, of course, if you really want to not stall after 500 cycles or 1,000 cycles or 2,000 cycles. But the model itself doesn't have a fundamental issue as to what should I do. You know what to do. You basically stall the load and the dependent instructions, independent stuff can execute. Okay, so I would argue that this is really the biggest reason why out-of-order execution, superscalar execution has been very successful, whereas VLIW has not. Okay, so, but let's talk about this philosophy and principles a little bit, and then I'll give you some compiler background also. But you can see that this is a paper that was written by Josh Fisher, who was the inventor of VLIW. And you can see the title, right? A smart compiler and a dumb machine. And that's really the philosophy, if you will, over here. Now, let me give you, this philosophy is actually very similar to what we have seen earlier, which is simple instructions, reduced instruction set computers, right? That philosophy is very similar to VLIW. VLIW extends it to multiple instructions per cycle, just like a superscalar extends a scalar processor to multiple instructions per cycle. So RISC, for example, in the 1970s, it was developed. John Koch was an IBM engineer who developed the earlier philosophy. He won the Turing Award for his work, actually, for this. And it was first employed in IBM 801, when IBM was actually at the leading edge of building real systems, if you will. Yeah, I already said this. Basically, the philosophy here was that compiler does the hard work to translate high-level language code to simple instructions. Instructions should be as simple as possible. No sophisticated instructions like matrix vector multiplication, even multiplication, actually. And John Koch took this to the extreme, actually. He said, compiler should be controlling the control signals. So the instructions should be the control signals, essentially, right? Which is a very different way of thinking. You expose every single control signal to the compiler, and this actually led to a lot of development in compilers. And compiler needs to reorder simple instructions for high performance. And that's basically what the philosophy of VLIW is also about. Hardware does little translation and decoding, so it's very simple. VLIW compiler does the hard work to really do this at the vertical side also. So RISC says basically at the instruction level and a pipeline level, horizontally, and VLIW says vertically within the same cycle you do that also. So basically vertically and horizontally is much harder than clearly just horizontally, right? So you need to do the hard work to find which instructions can be executed in parallel. Actually, even worse than that, which instructions can be executed when, at what time, and with which other instructions. And as a result, hardware stays as simple as possible and executes each instruction a bundle in lockstep. So why is simple? Why are people pushing for this? Clearly, simple hardware has some benefits, right? People believe, and this is most of the time true, actually, it's easier to design simple hardware. It's lower power in terms of total design power. It can be higher frequency, although you could make your hardware higher frequency with heavy pipelining also, but it comes at a cost. But basically, getting all of these at the same time is very difficult if hardware needs to do a lot of dependency checking, etc. But you can get all of these at the same time in a VLIW machine, in a RISC machine. But it comes at a cost, right? Basically, performance cost. I said simple doesn't provide performance over here. Performance is the job of the compiler now. The question is, can the compiler get that performance? So power is very interesting over here. I said power, low power over here. So simple hardware is low power. At any given point, it doesn't consume a lot of power. Now, if it's low performance also, that means that the program will run longer, right? If the program runs longer, much longer, even if you have a low power processor, you may be expending much more energy, right? So if you recall your physics, how many people have taken physics? Hopefully I'll see lots of hands over here. If you recall your physics, what is energy? Energy is instantaneous power times time. Well, more accurately, it's the integration of power over time curve, right? Every time point, you have some power that you consume every time, and you integrate the power over time, and that's the energy you consume. Now, you may have a very low power processor. If it's extremely low performance, the time is much longer than a high power processor, right? So, okay, maybe visualizing this it would be useful over here very quickly, even though this is going to lengthen the context switch penalty, as you can see. What do we do? DocuCam. I need to do something else also. DocuCam. Am I correct? And then not share. Thoughts? Is it good? Okay. So, okay, I mean, it's a simple example, but I think it deserves some visualization because this actually is interesting in my opinion. It's very fundamental, right? So you have a low power processor. This is the execution curve. It looks like basically this is instantaneous power, how much power you spent. It could be watts. And then this is time. And you execute one program, and low power processor may be something like this, right? Over time, it has some power. It's low power. And then the program ends here. Okay. What is the energy you spend? Energy you spend is the integration of this curve, power times time. Right? That's the energy, basically. That's the energy on low power processor. My terrible handwriting. Okay, at least I'm repeating it. High power processor on the same curve may look like this. The power is high, but the program ends here. Okay, what's the energy? You integrate this curve. So this energy actually may be smaller than this energy. Right. So in the end, if you have a much faster processor that consumes a lot higher power, it may actually be better for energy. So what is the implication of this? Energy is actually what determines your battery life in the end. That determines the draw, because you have your battery has limited energy capacity. And in the end, this high power processor that finishes your program much faster can draw some energy and then go to sleep, right? And then it doesn't consume any energy, whereas this processor consumes a lot more energy. Now, what's the implication? What's the downside of this high power processor? Well, supplying this power, right? Basically, this is, let's say you have a maximum power over here. It's called total design power for the high power processor. And then you have a maximum for the low power processor. And I made a mess over here. This is the low power processor, let's say maximum total design power. So this is low clearly, and this is high clearly. So here your power supply needs to be much more powerful. So this has implications on cost and power, etc., efficiency. So there are a lot of other implications over here. But this hopefully shows you that low power doesn't necessarily mean low energy. And low power doesn't also necessarily mean low cost. So even though this cost may be higher, here to get the same lifetime, you may actually need a much bigger battery, for example. Okay, so this is a sideline that I had to express over here because of what will come soon related to VLIW. But also this is more general than VLIW, this sort of trade-off. Any questions? Feel free to ask while I'm doing the context switch. So what do I do? Follow project D1? Is that correct for the... this goes to N2, I know, but I don't know what this does. Ooh. What is this? Okay, this I can fix, I think. Okay, that's fixed. I think that follow project D1, but yeah, it's okay, I think. I see picture. Okay, as long as it's okay on live stream also, we can move on. Is it good on live stream? Okay, I think it's good. Well, I'm not sure. Okay, somebody said yes, so I'm going to assume that yes, as opposed to looking. Okay. Okay, so now we kind of had an aside because of this. So simple doesn't mean low energy, basically. That's the whole point. That was the whole point of what I discussed. Simple also doesn't mean low cost. And simple definitely doesn't mean high performance. It does mean low power for the definition of total design power. Okay. Okay, so you can read this paper. It's beautiful, actually. It's very nicely written for a paper written in 1980s. I cannot say that for every paper that's written in 1980s, but I'm not going to talk about everything over here. We're going to distinguish VLIW more from SIMD later, but I'll give you a little bit of history. So people actually tried to build these VLIW machines. For example, Josh Fisher himself built the Multi-Flow company. They actually tried to build 28 wide, meaning you fetch 28 instructions per cycle. There are 28 instructions in a bundle. They built these machines. Unfortunately, they did not really become commercially successful. Bob Rao is another person who was at HP Labs developing, well, before he went to HP Labs, he developed the Sidra processors and Sidrome. They actually built VLIW machines. Again, these are startup companies. They tried hard. Unfortunately, they were not very successful commercially, if you will. Transmeta Crusoe, I'm going to talk about this briefly later on also. These folks were actually trying to do something very interesting. They were trying to compete with Intel at the time. They took x86 binaries, x86 code, because there's a software base, right? You take the software base and you translate it internally to a VLIW engine so that you can extract a lot of parallelism without the hardware cost with simple processors. And they tried very hard. Unfortunately, they were also not very successful, at least in the general purpose market. Where VLIW has been very, very successful is where you could actually extract this parallelism relatively easily in digital signal processing, for example, or embedded processors. You can see these were actually where VLIW was quite successful. And also power limitations, like total power limitations of these devices are relatively low. Whereas in a general purpose computing device, if people care about performance, you may not care as much about power. I want to get the highest performance, right? But in some of these embedded processors, total power limitations are low. And there's a lot of possibility to get parallelism out of the code using compiler techniques. So most successful machines were these. Even, for example, AMD and ATI GPUs were VLIW, but I'm not sure if they are right now, initially. So Intel is this is a very interesting story. When x86 processors were moving from 32-bit, Intel had a lot of discussions as to, oh, do we just extend the x86 ISA or do we come up with a new ISA, instruction set architecture? So Intel decided we're going to come up with a complete new architecture, instruction set architecture. We're going to ignore the software base, kind of. And we're going to move to this IA64 architecture, 64-bit, completely redesigned. It's not fully VLIW, but it's based on VLIW principles. It breaks some fundamental VLIW principles, meaning the instructions that are in a bundle, there could be dependencies there. But compiler tells which instructions are dependent, such that the hardware's job is easier. So this is a kind of a mixed model where compiler doesn't fully guarantee independence, but when it cannot guarantee independence, it tells the hardware, oh, these instructions are dependent or may be dependent on each other. So be careful, okay? So you can see there's a different model right now. This is called explicitly parallel instruction computing in Intel marketing terminology. Yeah, I've already said this. So basically, there are a few bits in the instruction format that specify explicitly which instructions in the bundle are dependent on which other ones. Okay, in the end, this was not successful. In the end, Intel, I believe, is not developing these processors anymore after a lot of effort went into it in terms of both software, compilers, hardware. But even a dominant company like Intel was not able to change the huge software base that was out there for x86. Well, why? Because there was a competitor, I would say. And that competitor was AMD. And what AMD did in this transition was they basically said, we're not going to change the ISA. We're going to develop x86-64. So if you've heard about x86-64, it's really AMD's instruction set architecture, which extends x86 with small extensions. It just adds 64-bit instructions, basically, instead of changing the execution model and the ISA completely. And Intel had to adopt that in the end, because otherwise they would lose. Because there's so much software base and nobody wants to really, well, nobody, I should not say nobody, but a significant fraction of people who are writing x86 code or already executing x86 code don't want to rewrite their code completely. Okay, so there's a lot of interesting things over here, actually. This is a very, in my opinion, this is a very interesting story. Okay, so people have tried VLIW, as you can see. So let's talk about the trade-offs. The big advantage of VLIW is there's no need for dynamic scheduling hardware. As a result, hardware is simple. There's no need for dependency checking with a VLIW instruction. As a result, the hardware is simple. No renaming also. There's no need for instruction alignment and redistribution after fetch to different functional units. As a result, hardware is simple. Basically, hardware is simple. That's the big advantage. The disadvantage is now lower performance. Basically, a compiler needs to find n independent operations per cycle, and also horizontally, don't forget that. If it cannot, what does it do? It inserts no ops. Once you start inserting no ops, you lose parallelism, basically. No op doesn't do anything. No op is a no operation. Right? No op basically says, I could not fill this slot, instruction slot. Okay, not good. As a result, you get parallelism loss, and also code size increases, because you need to encode those no ops somewhere. And actually, a lot of work looked at how to encode those no ops in VLIW, which is interesting also. So you could actually encode no ops very efficiently. Okay, another issue is whenever you change the microarchitecture or execution width, instruction latencies, functional units, you really need to recompile code. This doesn't happen in superscalar out-of-order execution. In superscalar out-of-order execution, somebody comes up with a beefier out-of-order processor. It increases the fetch width, execution width. Software doesn't need to care about that, right? Hopefully you get higher performance without anybody changing any software anywhere in the world. Whereas here, if you really want to get higher performance, you need to compile the code. If people did not really take into account the fact that hardware will change and the ISA was strict, your code may not even run in the new hardware. So you have a problem, basically. And then lockstep execution causes independent operations to stall. No instruction can progress until the longest latency instruction completes. And this is, in my opinion, the real worst part. You can handle the first one, maybe. You can handle the second one, for sure. The third one, very difficult to handle, as we discussed, right? The variable latency operations. So basically, to summarize, VLIW simplifies hardware, but requires very complex compiler techniques. And as a result, the solely compiler approach of VLIW has several downsides that reduce performance. The most important of which we discussed, no tolerance for variable or long latency operations because of this lockstep execution. Too many no-ops because the compiler may not discover enough parallelism. You could alleviate that with more sophisticated techniques. The first one you cannot alleviate, sorry. The second one you can try to alleviate, somewhat successful depending on the code. The third one also is a nuisance, basically. You have to live with, basically. Static schedule is intimately tied with microarchitecture. Code optimized for one generation performs poorly for next, unless you recompile it, basically. So all of these three are actually bad, but the first one, there's no solution, if you will. Third one, there's no solution, but you could be smarter about it, maybe. Okay, so why are we talking about this? We are talking about it because this has been extremely influential, actually. I'm going to give you some examples. A lot of compiler optimizations have been developed for VLIW in optimizing compilers. If the optimizing compilers you use VLIW optimizations for superscalar compilation, because superscalar processes also benefit from this. If you have independent instructions that are discovered and put together, you don't need to stall, right? If you feed it into a superscalar processor, it already is able to process things in a simpler way. It does dependency checking, but it kind of wastes that hardware, if you will, if the compiler did a good job. So this people have enabled a lot of code optimizations, as we will see soon. And VLIW is also very successful when parallelism is easier to find by the compiler, especially in very simple static codes, embedded markets. Automotive market used to be like this, for example. It's changing. Digital signal processors and initial GPUs. Modern GPUs are general purpose. So once you start more general purpose, you start executing a lot of code and it becomes irregular. So if you confine your application space such that code is relatively regular, predictable, etc., it has been extremely successful. That's why in the embedded markets, it's been successful. So let's talk about these compiler optimizations. I'll give you an idea of what compilers do. These are basic blocks. This is from the paper that I mentioned. These are basic blocks. Remember the basic blocks that we looked at when we did basic block reordering? This is some code, and then there's a branch. This is a taken path, not taken path, and then there's some other code, and then there's another branch. You can see that this is a complex control flow graph. What VLIW compilers do is they try to find the frequently executed path in this, and they form a trace, if you will. They merge the code here, assuming that that's going to be executed together. That's the assumption. And they optimize the code very heavily, reorder instructions, find independent instructions, etc., assuming that that's the only code you're going to execute. Now you can optimize a lot, right? So you can have hundreds, maybe thousands of instruction blocks. Whereas if you look at a single basic block, it's 5 or 10 maybe instructions, right? Now, of course, when your assumption is wrong, it's bad. You need to modify the control flow graph. When you go out, you need to re-execute or change the execution. Basically, you should undo what you've done based on your assumptions. This is called fix-up code, and this is the fix-up code that they show in this paper. So your code size actually increases significantly, but the hope is that if your program executes this path, almost always, you almost always execute very highly optimized code. And this is the fundamental principle behind just-in-time compilers also. The dynamic compilers all do this. They figure out the frequently executed paths of code, the Rosetta, for example. Whatever dynamic compiler you may be using, they all do this. They figure out the frequently executed path, and they assume it's going to execute, and they fix up the code if that assumption is not correct at runtime. And if the assumption is correct, which means that your profile input set was representative, that's great. You execute very heavily optimized code. Okay, we're going to see a more, let's say, less high-level example very soon. And I'd recommend this paper because it talks about this. So if you think about this, we've covered some of these concepts earlier also, right? The basic concept that we've covered in an earlier, very recent lecture actually, was basic block reordering. Do you remember? Basically, we were trying to do branch prediction, and the simplest branch prediction mechanism is next fetch address is PC plus 4, right? Not taken, basically predict always taken. And we said you can reorder the basic blocks to actually make this more successful. So we're building on that actually. Basically, likely taken branch instructions are actually a problem. They hurt the accuracy of always not taken branch prediction, and we tried to solve that. But actually, branch instructions make static code reordering and scheduling difficult. So we want to get rid of branch instructions, or at least the taken branch instructions that take you somewhere else. Right? You really want straight line code, if you will. every instruction that's executed is the next instruction, next sequential instruction. This is good for branch prediction. This is good for compilers, code optimization as well. So we're now combining multiple concepts. So what was basic block reordering? If you remember, the idea was to convert the likely taken branch to a likely not taken one by reordering the code. So by reordering the basic blocks after profiling. So what's a basic block? Just to remind you, this is code with a single entry point. Whenever you enter code, you execute whatever is inside this basic block, and then you exit. You exit to one other basic block or this other basic block, right? It could be a branch. So you're guaranteed to have a single entry and a single exit. And these are very good blocks. If you have a single entry and single exit block, and you're not exiting or entering at any point in that, you can optimize the code beautifully because there are no branches. You know that once you enter, you're not going to exit unless you have an exception or an interrupt. Now, this is where we tie to the exception and interrupts lecture. Right? This huge code. If that code is 10,000 instructions, that's great. The compiler can look at all those 10,000 instructions and say, here's how I'm going to schedule this 10,000 instruction block. Beautiful. Okay, so this is good for branch prediction also, obviously, because you can do always not taken. Right? So this is a control flow graph. I actually drew this in the DocuCam, but this is our control flow graph I showed you. One branch is taken 99% of the time this way. The branch is not taken 1% of the time this way. How do you lay out this code? Basically, if the code layout is this way, if you actually change the branch in some way such that it's not taken 99% of the time, you execute A, B, D, right, as straight line code. So code layout 1 leads to the fewest branch mispredictions. This is what I showed in an earlier lecture on the DocuCam. Code layout 2 is bad, assuming your profiling is correct, right? So code layout 1 says branch is not taken 99% of the time, basically. So this is straight line code. This is good for branch prediction, clearly. This is also good for optimization of code. The compiler can assume that this is the code that's executed. Okay, now we're going to take one more step. So people said, okay, we're combining, we're basically laying out code such that the frequently executed path is always the next sequential path, right? That's what we're trying to do, really. Why not expand the scope? Here, the scope is only this, right? So let's expand the scope. Why don't we combine these frequently executed blocks such that they form a bigger block? This is called a superblock, perhaps unsurprisingly, but this is used in your compilers. In fact, existing compilers use hyperblocks, etc. But you combine frequently executed blocks such that they form a single entry, multiple exit larger block, which is likely executed as straight line code. So I'm going to give you this example in the next slide. So the big benefit is you reduce branch mispredictions this way because you're almost always executing straight line code, and you enable aggressive compiler optimizations and code reordering within the superblock. I'm going to give you a very simple example soon. The downside, of course, it always comes with a downside. You increase the code size, right? Why do you increase the code size? You need to add fix-up code, as we will see. It requires recompilation, and then the killer is profile dependent. If the compiler doesn't have the good enough information about dynamic execution, you optimize one path, dynamically you execute some other path. And then once you execute that other path, it's actually probably worse than not optimized code. Why? Because you're executing something totally irregular right now. Compiler actually added more irregularity to those paths. Of course, you can try to fix this by optimizing multiple paths. Now it becomes much more complicated. Okay, so now you can see the difficulty in static scheduling, right? And you can also perhaps more appreciate why out-of-order execution has been successful. It avoids all of these. But out-of-order execution also benefits from this when it works. Okay, so that's the important thing. So let's take a look at the superblock formation, this more complicated control flow graph. So you have an entry to the loop, and this is the exit to the loop, and you can see that this is a loop. And then there's one basic block. There's a branch that's taken 90% of the time this way, and then 10% of the time this way. And then this branch over here is taken 0 times this way, 90 times this way. These are absolute counts. This branch over here is executed, well, it's an unconditional branch 10 times. And these are unconditional branches, as you can see. So basically, you have frequencies on the path over here. And this loop branch is taken 99% of the time. So if you look at this is the frequently executed path in this loop. This is what you would like to optimize ideally. So if you want to form a super block, you essentially combine these blocks. Now, this is not a super block yet, because this is not single entry, multiple exits. There are multiple entry points, right? You enter from here and you enter from here. We're going to eliminate that. This is a trace, actually. This is what original VLIW compilers did and optimize these traces. And you can get somewhere using these. Now, how do you make it a super block? You add a little bit more. Now, basically, you should make sure that you do not enter the block anywhere other than the top. So you need to basically take this D. When you exit the block, 0 is the profile, but in real execution, this may not be 0. 10 is profile. In real execution, this may not be 10, but it doesn't matter. You need to make sure that the code executes correctly still. So if you exit to D, you should not re-enter here. Because if you re-enter, you're hindering some code optimizations. If you actually you don't have straight line code basically anymore. We really want straight line code all over this over here. So basically what you do is you duplicate the tail. If you exited the superblock, you always stay out of the superblock. So we have another F bar over here before going into Z. If you exited the superblock at C, you always stay out of the superblock. So we have another F bar. You have the same F bar. So that's called tail duplication. And this is one example of duplication of basic blocks to ensure that you don't have these side entrances to the superblock, such that the compiler can nicely optimize the superblock. So this is really the superblock. And this is code with single entry point and multiple exit points, as you can see. So again, we can go into a lot more detail over here, but then you need to take a compiler's course, which is fascinating also, in my opinion, but this is not a compiler's course. So basically, the whole point is that you can optimize the code once you make it straight line like this. But if while the code is executing, you exit out of the straight line code, you execute some other stuff, let's say, that needs to be added by the compiler. So let's take a look at one potential optimization with a very simple superblock. This is your original code. I've eliminated the branches because they it's nice to look at branches. This is your operation A. This is your operation B. This is your operation C. These are 3 different basic blocks. There's a branch here. 99% of the time, it goes here. 1% of the time, it goes here. And then there's another branch, unconditional, that goes here. Basically, if something, do this. Otherwise, just follow straight line code. That's what this branch does. Now, after superblock formation, this is what happens. You basically combine the 99% path, these 2 instructions. You can reorder them nicely if you can. And then once you exit, you have this code, but then you cannot re-enter back. So we want to eliminate this edge, so we duplicate this tail. That's the tail, essentially, duplicate this instruction. So we have 4 instructions now in this very, very simple example. This is the simplest example of superblock that I can, let's say, come up with to show something really interesting. A really interesting thing happens next. Now, what do you see over here? This multiply and this multiply are doing the same thing, right? On the frequently executed path, you don't need to execute this multiply. You can basically reduce the strength of it to a move. So, but this is called common subexpression elimination. The subexpression is R2 plus 3, or R2 times 3, R2 times 3. Compiler figures this out, says this multiply can just take the register value R1 and copy it into R3. Now it's beautiful. Even with this very simple code now, we've eliminated a multiplication, which may take 8 cycles. A move is going to take, a move is a simple operation, basically. It doesn't even do calculation, right? So that's the beauty of compiler optimizations, as you can see, right? Even with this very simple code. But the trade-off is there. You used to have 3 instructions, now you have 4 instructions. Okay, so if you're interested, there's a lot more over here, and we don't have time to cover them. But people have developed a lot of compiler optimizations, essentially. And they've been very useful for out-of-order execution, superscalar execution as well. So there's more. We will see tomorrow the memory banks. So it becomes hairy, basically. At the compiler level, you can do this. But whenever you need to reorder code, one problem happens. How do you reorder store over a load? You have a store instruction and you have a load instruction. And load instruction is earlier in the code, in the original code, and the store instruction is later. Can you reorder the store earlier, for example? And this becomes a huge issue, basically, because you don't know the address of the store again, or the load, until, assuming it uses an addressing mode that's dependent on dynamic execution. Most of the loads and stores use addressing modes that are dependent on registers, let's say. So compilers need to be extremely sophisticated for this. And that's another reason why even code reordering is actually not so easy. Okay, there's a lot more on static instruction scheduling that we're not going to cover. I'll refer you to these. But you can see that this example has, let's say, stood the test of time. I think this is the best example. If you come up with a better example for benefit of this forming larger blocks, please let me know. Okay, let me conclude with some things on ISA translation, and then we're going to take a break. But remember, we've also discussed translating of ISA. You can translate from one ISA to another internal ISA to get a better trade-off space. You can have a programmer visible ISA, virtual ISA, translate to an implementation ISA, complex instructions to simple instructions. In other words, scalar ISA to VLIW ISA also. And that's what people have tried to do as well. So for example, Intel AMD's x86 implementations translate x86 instructions into simple instructions, CISC to RISC, let's say. And Transmeta's x86 implementations translate x86 instructions into secret VLIW operations in software. So they did all of it in software. So these techniques that I just discussed, more sophisticated ones, were employed in what they call the code morphing software. And they had a lot of trade-offs. So this is what they looked like, basically. Outside, the operating system was x86, applications were x86, and then there's a BIOS. Internally, everything went through this code morphing software, which is essentially a dynamic binary translator, which translated everything to a proprietary VLIW ISA. And they actually built these processors. Unfortunately, they don't build them anymore. And this is an example of the semantic gap. I will not go into this in detail again, but basically, they changed the semantic gap trade-off by having a small semantic gap between the high-level language and x86 over here. But then they use a software translator, dynamic optimizer, that did a lot of optimization similar to what we discussed, to turn that code into a VLIW code. And then the hardware can stay simple. So you don't change the huge amount of software that's written in the world. That's good. You put a lot of effort into, a humongous effort into the software translator. The hardware is simple. That's the good part. So software, translate, and hardware can all perform operation reordering in the end. And as I said, unfortunately, they were not successful. What has been successful is this. They've actually done a great job, in my opinion, to do something very similar to a more complicated ISA. They were able to translate x86 to ARM. And this binary translation, if you look at the structure of what's not advertised, it's going to look very similar, basically. Except this is x86, and this is not VLIW, but it's ARM. It's the Apple's ARM ISA, basically. Okay, so NVIDIA Denver did something similar, and you can read about it. So if you talk about these, and again, I don't have time over here, but I will mention this one. DCO is the dynamic code optimization software. And NVIDIA says co-designing a hardware processor with a dynamic code optimization software system creates both additional validation exposure and benefits in addition to what we've discussed so far. The DCO system can be upgraded in the field to address functionality, performance, or security issues. And they don't tell much more about that, but it's true, actually. You can upgrade your software without changing the hardware underneath. Okay, there's a lot more to cover, and we don't have time. But if you're really interested in compilers, this gives you hopefully a glimpse of it. How many people have taken anything about compilers here? It's too early, of course, I know. Yeah. Now you're exposed a little bit. Okay, so this is where we will take a break, 10-minute break. So we'll be back at 15:18 to cover another, let's say, big concept.